Physical properties of matter don't rely just on bonding. We also need to consider structure as well. They need to tie together to enable us to understand some of the physical properties of various bits of matter. So, for example, if we take metals, the metals tend to have high melting points and boiling points. The reason for this is that we have strong metallic bonds. But it's not just the strength of the metallic bonding that's the important thing. It's the arrangement of those bonds that we have. And we have a giant structure with metals. So we have giant metallic structures. That means that the strong metallic bonding extends throughout the lattice structure without any breaks at all. So therefore, to melt our metal, we will need to break strong metallic bonds. And we find the idea of giant structures extending not just through into metals, but through ionic compounds and covalent compounds as well. So, for example, ionic compounds tend to be giant lattice structures once again, and the arrangement makes a certain amount of sense if one considers a cation. Now, a cation is going to attract an anion, but it's not going to attract it just in one direction. It's going to attract anions in all directions: left, right, up, down, front and behind. And of course, each of those anions themselves are going to attract cations, and we're going to build up a lattice structure where anions attract cations, which attract anions. And one can imagine that this again will extend throughout the lattice structure without a break. So we talk about giant ionic compounds, high melting points and boiling points once again. We can think about covalent compounds. Now, a covalent compound in a giant structure again will have covalent bonds, and these covalent bonds, directional in this particular case, 4 covalent bonds in this particular case, whereas with ionic and metallic, of course, it's attracting and repelling in all directions. But here you can imagine that you have 4 covalent bonds with 4 atoms attached to those covalent bonds. But each of those covalent bonds will themselves have covalent bonds attached. And we can build up a giant lattice structure where we have these strong covalent bonds extending throughout the lattice structure without a break. So a structure like this would have a high melting point. But covalent compounds exist in other forms apart from the giant or macromolecular structures. We can also consider what are called simple molecular structures or simple molecules. Now again, we can have a crystalline structure. In other words, a lattice structure, a regular arrangement of these molecules. And these molecules, of course, will have strong covalent bonds within the molecules themselves, holding the atoms together. But we're also going to have weak intermolecular forces holding the molecules, or the forces between molecules, holding the lattice structure as a whole together. And under those circumstances, we're going to have low melting points. Whereas with a giant covalent structure, it has a high melting point because covalent bonds, those strong chemical bonds, need to be broken. With a simple molecular structure, those strong covalent bonds remain intact, and it's the weak intermolecular forces that can be disrupted to melt a solid or convert a liquid into a vapor.